On Valentine's Day, 1990, a camera shutter clicks. Every photograph is unique, but the image captured at this particular moment is unlike anything that's been seen before, or will be seen again for many years to come. It is of the Earth, from 6 billion kilometers away. The last glimpse of home for the Voyager 1 space probe, venturing into the darkness, never to return. Voyager 1 has been on a grand tour of the outer solar system. Since its launch in 1977, it's flown past and photographed Jupiter and Saturn before heading out into interstellar space. But before it leaves, its onboard cameras capture a family portrait of 6 planets, including the Earth. It beams back the images encoded in radio signals. Travelling at the speed of light, the signals take 5.5 hours to reach us. It's the last photo the probe takes before its cameras power down forever. This photo of the Earth is not what you might expect. Diagrams of the solar system rarely show the planets and their relative distances to scale. In Voyager 1's image, made up of 640,000 pixels, our planet takes up less than 1. In this picture, Earth is nothing more than a pale blue dot. This fraction of a pixel contains every living thing that we know of, from bacteria to blue whales. It contains endless marching forests and grassy savanna. It contains more than 5 billion people and their sprawling cities on almost every continent. But from this far away, all of this life is invisible. Earth is a pale blue dot, a blur of deep blue oceans and white clouds. From this far away, our home appears as empty as the barren planets in our solar system family. But is this really true? Is the evidence for life on our planet so easily masked by mere distance? Would our home pixel really look the same if life had never come about in the first place? On Earth today, living things surround us. They're in the rocks, in the air, in the oceans. The planet is teeming with life. But as far as we have yet discovered, this is a rarity in the cosmos. Is life really so unlikely? In 1953, German-born physician Hubertus Strughold was contemplating the medical challenges of space exploration when he coined the term ecosphere. The ecosphere is a habitable zone around a star in which conditions are sufficiently temperate for life to thrive. By venturing away from the ecosphere, astronauts would find it incredibly hard to survive. By definition, Earth sits within the ecosphere, or habitable zone around our star. But since Strughold's revelation, astrobiologists worldwide have tried to identify the criteria for a planet to become home to living things. Of course, these criteria are based on what we know about terrestrial life and basic chemistry. That's the best we can do with a sample size of 1. First, the star must be suitable. It must be long enough lived to allow planets to orbit with stable conditions for a few billion years. Out of all the stars in our galaxy, about 90% make the grade. Then, the star must have rocky planets orbiting around it. Solid surfaces help the chemical reactions of life, so although it's possible for living things to be entirely airborne, it is much more likely that life got started on a solid, rocky surface. Not only that, but in order to sustain life's chemistry, the planet needs liquid water on its surface, and an atmosphere that is neither too thin nor too thick and crushing. To have a planet of just the right size orbiting within the habitable zone of its star, where it's the right temperature for water to linger as a liquid, is incredibly rare. Scientists estimate between 5 and 50% of Sun-like stars will have a planet like that. Still, in our galaxy alone, that leaves the potential for several billion planets, just like the Earth. Is life on these planets inevitable? Unfortunately, that's not an easy question to answer. We just don't know enough about the early conditions on Earth and the chemical revolutions that led to the first life. We don't know if, given the right mix of chemicals, life sprang up spontaneously all over the globe, or if it took a remarkable stroke of luck in one isolated pool in one corner of the planet. With this huge unknown, we can't say if life is assured, or if it's 1 in a billion. But since the origin of life still eludes us, there's a good chance that it's not easy or inevitable. Dedicated scientists still haven't recreated those earliest living things from non-living matter, so maybe life on Earth was, in fact, a fluke. If life on Earth came about because of a lucky roll of the chemical dice, then it's much more likely that it never started at all. How then would the planet have evolved over 4 billion years without life? How different would it look today? No people, no cities, no birds in the sky, no fish in the sea, no crawling insects. No plants, no trees, no grassy savanna, no mossy rocks, no seaweed on the shore. Far from a world daubed liberally with green, we'd be faced with a hard, harsh landscape of grey rocks and dark blue oceans. But the absence of life goes much deeper than what we see on the surface. In fact, some argue that there's nothing at all on our planet that hasn't been affected by living things. The surface itself is sculpted by life. Plants, from the most basic lichens to the biggest trees, are rooted to the land surface and modify it in turn. Root systems probe into the finest cracks, take hold and tear solid stone into shattered debris. Water penetrates the surface of this new rubble, dissolving minerals which the plants absorb. In this way, the compositions of the rocks at the surface are permanently altered by biological weathering. The result is a new kind of material which wouldn't exist at all without life. Soil. As well as the weathered rocks, soils contain an abundance of organic matter too, both living and dead. So if life never evolved on Earth, there'd be no soil on the surface today. Instead, the land surfaces of Earth might look more like those on the dusty red planet Mars. Although soils may seem like a minor loss from our planet, this thin layer has had a major effect on the shape and longevity of surface features. Because up to 50% of a soil is made up of voids, empty space which can be filled with water that helps the rock fragments and organic matter stay stuck together. Combined with the root systems that formed them in the first place, soils are incredibly good at staying put and protecting the unweathered rocks beneath them. Without soils, we could say goodbye to rolling hills and valleys. The landscape would be a hard, harsh one of craggy mountains, deep gorges, and chaotic rockfalls and landslides, altered by vast tectonic forces and the inexorable grind of water, wind, and ice. The rocks exposed at the surface would be fundamentally different too if life had never arrived. There would be no fossil shells or bones, no coals, oils, or natural gas either. Around 10% of rocks exposed at the surface today are limestones, formed from calcium carbonate which, almost always, has been created by living things. Mollusks, corals, and tiny plankton all make their shells from calcium carbonate. Without life, there would be no white chalk cliffs of Dover or marble quarries of the Italian Dolomites. But it's not just the solid surfaces of Earth that life has transformed. Living things have fundamentally altered the planet's swaddling atmosphere too. Before any life arrived on the early Earth, the atmosphere was a concoction brewed in the belly of a volcano. Carbon dioxide, water vapour and methane all spewed from the hellish molten landscape of the Hadean. But life, and especially green life, changed all of that. Photosynthesis, which transforms water and carbon dioxide into sugar and oxygen using light as an energy source, was a revolution for the Earth's atmosphere. This new chemical pathway was seized with fervour by living things about 2.5 billion years ago. The carbon dioxide that was so abundant in the early atmosphere was a bottomless feast for the first green organisms. They absorbed it and excreted oxygen in its place. And then they absorbed some more to build their shells, creating limestone rock. And so the atmosphere transformed from one dominated by carbon dioxide and methane to one rich in oxygen instead. Had life never gained a foothold and figured out photosynthesis, our atmosphere would be the same steamy volcanic effusion that reigned in the Hadean, dominated by physical processes and spontaneous chemical reactions. And indeed, today, a visitor to a lifeless Earth would find an almost unrecognizable planet. With a palette of colours closer to Venus or Saturn's moon Titan than the blues and greens and whites gifted us by life. Without oxygen in the air, it's not available to react with surface rocks and sediments. Much of the red colour we see in dunes and in river deposits is a result of iron minerals reacting with oxygen to make iron oxide or rust. Without life to make the oxygen to make the iron oxide, the surface of the planet would be painted in little more than shades of grey. Without reactive oxygen, methane can stick around in the atmosphere too. And when sunlight hits methane, it makes hydrocarbons. Not enough for life, but enough to make a sickly orange haze that fills the atmosphere with a permanent smog. All over the surface of the Earth, the sun would be veiled, as if by some approaching wildfire or distant volcanic eruption. Incredibly, a lack of life also means a lack of clouds too. The tiny creatures whose calcium carbonate shells make up the white cliffs of Dover also emit chemicals into the air that helps water condense into droplets and make clouds. They're so abundant in the oceans that they're a major contributor to our cloud cover. Without them, the planet may never be graced with the wisps of white cirrus or banks of fluffy cumulus. Instead, only an indistinct humid fog would lie, heavy beneath the overlying methane smog. In fact, had life never modified our atmosphere, the Earth may have suffered a similar fate to our planetary neighbour, Venus. Carbon dioxide is a greenhouse gas, trapping the sun's heat close to the surface. With an atmosphere full of this potent insulator, surface temperatures gradually rise until they reach truly hellish levels. The surface of Venus bakes at more than 450 degrees Celsius, due in part to its thick blanket of CO2. That could have been the Earth without life. It seems we may have life itself to thank for keeping our planet livable. The curious reliance of our planet's habitability on its living inhabitants was a paradox first noted by English scientist James Lovelock in the 1970s. Lovelock is something of a contemporary polymath, having worked in medicine, chemistry, and environmental science. In the 1960s, he considered how life might be detected on Mars. One of the most promising signatures, Lovelock concluded, was non-equilibrium. Only life has the power to drive atmospheres away from chemical equilibrium, just as on Earth reactive oxygen came to replace carbon dioxide. Finding an atmosphere out of balance suggests an invisible hand at work. By extension, he noted how the conditions on the Earth influence its biosphere, and how living things have the power to affect the Earth itself on a long-term global scale. The result, he saw, was a self-regulating system that keeps conditions stable and suitable for life all over the planet. A superorganism of sorts, on a planetary scale. He named his theory of a protective, self-sustaining feedback loop after the Greek goddess of Earth, Gaia. And Lovelock's Gaia works in many different ways to unconsciously keep the Earth habitable. To demonstrate the power of a self-preserving planetary superorganism, Lovelock and others conceived of a computer simulation of a theoretical planet, which is home to two populations of daisies. Black daisies and white daisies. It was called Daisy World. Black daisies liked it when it was cooler, and white daisies when it was hot. In the planet's early days, when the heat from its young sun was weak, the black daisies thrive and cover the planet. Their dark colour helps to absorb the sun's heat. Soon, it becomes warm enough for white daisies to take over. Their bright colour reflects rather than absorbs the sun's energy, and the planet temperature drops. Black daisies take over again, and eventually an equilibrium is reached, with both black and white daisies helping to keep the planet's temperature optimal for both populations. Daisy World is an incredibly simple model of a planetary feedback loop, and the Earth is certainly a much more complex system, but similar feedback loops have been affecting conditions on the planet over geological timescales. Take, for example, the carbon dioxide in our atmosphere. Volcanoes emit carbon dioxide, causing levels of the gas to rise in the atmosphere and increasing the thickness of our warming blanket of gas. Temperatures rise. Warm temperatures are good for life in general. One need only to look at the tropical rainforests to see how living things thrive when it's warm. So when the Earth is warmer, plants grow faster and denser, and all these plants need carbon dioxide to fuel their photosynthesis, so they draw it down from the atmosphere and lock it away in their tissues. Some is returned to the atmosphere, but much of it is sequestered away in the long term, in other living things, or in soils, or in the rocks themselves. By reducing the amount of carbon dioxide in the atmosphere and thinning the blanket of greenhouse gas, living things have ensured that the Earth doesn't get too hot. And there's a check at the other end of the scale too. If carbon dioxide levels drop too low, the Earth's temperature will also drop. Colder, ice-covered landscapes aren't hospitable to life, so plants don't thrive. There aren't large populations to hoover up carbon dioxide, so over time the gradual input from volcanoes can boost levels until temperatures start to rise again. In this way, carbon dioxide levels and temperatures have fluctuated through much of Earth's history, moderated by living things. Regulation by the guiding hand of Gaia never sees conditions pushed too far. And Gaia's mechanisms don't just see temperatures maintained. The complex interaction of organic life with the inorganic Earth helps to keep the chemistry of our oceans in check too, helping salinity and acidity stay at the same levels for hundreds of millions of years. Gaia's guiding hand has no consciousness behind it. It is but a fortunate consequence of our life's colonization of Earth. It's this link that has kept Earth habitable and inhabited for billions of years. An ecosystem that doesn't promote the conditions of its own survival is not destined to last long. And yet, in the last 100 years or so, humans, as the newest life form on the scene, are testing Gaia's ability to bounce back. The changes that we have wrought on our planet have been faster and more extreme than anything Gaia has yet faced. Carbon dioxide levels have risen and global temperatures have soared. It remains to be seen whether our ecosystems can adapt to compensate in time before the planet roasts. When Voyager 1 pointed its cameras back at the Earth in 1990, it saw a blurry, pale pixel. The life that graces our planet is invisible from 6 billion kilometers away, but its effects on the globe are not. That our oceans and clouds persist at all is a sign that temperatures are still optimal for surface water. And that is thanks to life and Gaia. Next time, we will explore the fascinating stories behind the first fossils and the origin of Earth's magnetic field. You've been watching the entire history of the Earth. Like and subscribe, and we'll see you again soon.